lecture capture. So okay, so it's the lecture is captured. So just an announcement: we're reviewing second lab, which is focused on mechanical properties of metals. So each group will receive or have received and analyzed a ferrous material and a non-ferrous material of metals. And you were required to map the strengths of materials, draw a stress-strain diagram, and also analyze the major components like ultimate tensile strength, ductility, at elongation, ductility at necking, and also plot engineering and true stress-strain diagrams, and also answer questions relative to the fracture behavior. And then there were individual questions that would really probe your understanding about whether there is sufficient knowledge to reflect on the data obtained in the lab. Okay, so let me step back and look at the samples that you had. So you had one ferrous material, and you either would get a stainless steel or you get annealed low carbon 1020 plain steel or cold rolled as processed plain steel. So these samples are shown on the left in the main diagram or in the main slide which I have. Okay, the stainless steel is the tallest. It's the most stretchy metal we have. So as I mentioned in the lecture slides, that don't be tricked as an engineer that stainless is good. I mean, it's a great steel. I mean, for lack of a better word, it's an excellent non-ferrous material. It's corrosion resistant, it's ductile, which means that you can process it. There are some difficulties with welding stainless steel, but there are ways to do it. But in a way, it's a weak material. So unless stainless steels are used as high alloy steels, so those steels that have a lot of additional components in them, such as chromium, vanadium, nickel, and silicon, then those steels, like cheaper stainless steels, they're inferior in their mechanical properties. They're easily bent, they're too stretchy, they're too ductile, and this is what exactly you see on the slide. The stainless steel elongated the most, okay? And it also formed a relatively uniform stretching area, okay? So you now can contrast it relative to plain low carbon steels. And by the way, stainless steel will have some carbon, okay? So generally it's like less than 0.5%. So it almost like those steels, which are second and the one in the middle, but with nickel or chromium added to that, okay? But the stainless steel that we had, it was not necessarily lower quality. It's 304, just one of the run-of-the-mill type of stainless steel, which is used as construction type material. Okay, so what you could see, just even visually, that the annealed steel or 1020 has been heated and then left to cool down. With heating and cooling down, the stresses are released and the steel become relieved. So it's relaxed. And it actually shows slightly longer elongation compared to plain, untreated, or as processed cold rolled steel. Then you also had one sample which is non-ferrous. It was either copper or it was aluminium. Aluminium is the furthest to the right, and copper is the reddish sample you have. You see, quite surprising. Like we always think that, you know, if you take an aluminium wire or you have an aluminium foil, it's sort of very crumbly, right? Like if you handle aluminium parts, they seem to be pliable. but they're actually very brittle, which is quite surprising. Okay, so, and this is like when you contrast and compare coupons, it's quite visible. Okay, so let's walk through what you did, and I'll comment, I'll read through the sections in the lab, so I've got the labs to mark. So what we have, the first task, you had to measure dimensions across the gauge length, and all of you did well. Okay, you had to take the length, you had to take the width, and you had to take the thickness, so, which is perfectly fine. What I noticed through marking is that when students were using millimeters, like the most convenient way to actually take the measurements, they made far less mistakes in calculations when they were trying to convert to meters. Because when you use meters, then dimensions will become tiny. And it's very easy to get entangled in zeros or orders of magnitude. Okay, so using millimeters were easier to work with. Then running tensile tests, everything was great. So, I mean, you could collect load at the UTS, so all the results were correct. So basically what you would have is, let me see if I can I draw? Okay, maybe I can draw let me see. Okay, maybe I will just create a new slide and just a new blank slide and turn on. Okay, so then we can walk through. So I'm drawing using my mouse, so please excuse me for being a bit sort of crude and cumbersome with it. So what you will have is this is your force versus extension diagram. So normally what you would have something like this for two of the materials. You will record a maximum force, which is going to be force at ultimate tensile strength for different two materials, and you will also get strength at fracture. What is important is that the strength or the force at fracture should be lower than the UTS. So it generally, this is the rule, because as materials will form a neck at the UTS point somewhere here, then the cross-sectional area is reducing. So the neck will shrink the cross-sectional area and less force is required. So therefore, the force at fracture will be less than UTS. Okay, so as long as force at UTS is larger than force at fracture, you'll be fine. Okay, so I have not seen any errors so far. So this is the major rule that you would generally comply with when you would run experiments. So task 2 was completed well, and then you also needed to record, look at the samples as they would be fractured, and look at the fracture zone. So let's say this is the fracture, and you would need to take dimensions at the thinning area. So somewhere really at the necking area, and you take width, and you take the thickness, and you will also take the gauge length at fracture. So, and by that, you would be able to proceed later with running the tasks in the lab. So the gauge length at fracture is needed to then work out the strains on the X, the strains for both materials. And the cross-sectional area is also needed to work out percentage of reduction cross-sectional area. This is what the necking will give us. And the changes in gauge length will also give us percentage elongation. So most of you have managed well, and you got really reasonable data. So what you would see is that if I would go back, for example, and back to the samples, what was surprising, I think, like when I started working with materials, what surprised me first is that I didn't know that non-ferrous materials are brittle. Like, to me, it was a bit of a revelation. I thought that, you know, when you have a copper wire, right, so you can easily bend it and you can easily turn and twist. And because you apply less force compared to working, for example, with like chicken wire, right, it gives you a false sense of indication that it's more ductile. But it's actually wrong. Okay, the fact that we're using less force to mangle it, it doesn't mean that it's more ductile, like when you actually measure it physically. And the same happens with aluminium. For example, you take an aluminium sheet, or you can have an aluminium can, or any of the aluminium parts, or a bar, or something, and you can bend it really easily. You can crumble it. And the fact that you use less force gives you a false sense of assurance that it's more ductile and it's more pliable. Actually, it's wrong. It's more brittle. Okay, so this is something of a learned experience. So as engineers, please be mindful that steels, actually, they could be superior, not necessarily all, but they could be superior to non-ferrous metals in terms of the ductility and necking behavior and general ability to withstand force, like high force, and actually cope with a lot of deformation before breaking. Okay, that's why steels are used in majority of engineering components, simply because they're quite forgiving, and they're quite forgiving to abuse. Okay, so then we proceeded to task 4, where we need to get the reference values from the blue sheets for ferrous and non-ferrous materials. So you would need to get a Young's modulus, everyone done it correctly, well, majority of those reports that are marked, so everyone done it well, and then the yield strength. And based on that, you would use an approximate coefficient to find out what would be the length at UTS, or length at the necking. This is where the majority of you made actually mistakes. The reason is that, you see, I've started the conversation saying that, look, we, through nature and through exposure, we have this slightly wrong, skewed assumption that metals are more brittle. I mean, that steels are more brittle than, for example, copper, aluminium. And for that reason, some of you have used wrong type of coefficients, like, for example, not using 0.8, but using 0.9 or vice versa. It's not a critical factor, but that would skew your results onto the more wrong end of data. Okay, not a major error, but nonetheless still an error. So something to be mindful about. So, for example, when you would look at task 3, where you would estimate percentage elongation, which is ductility across the whole sample, so from nose to tail. That's the what percentage EL means, because you actually look at the gauge length. And then you would estimate percentage reduction of cross-sectional area, so taking the sample width and thickness before the deformation, and then once it's failed. That value, percentage reduction of cross-sectional area, is really the shrinking within your necking area. Okay, and what you would see is that more ductile materials will have both larger percentage EL or larger longitudinal elongation value in magnitude, but also larger magnitude in percentage of reduction of cross-sectional area. So they both elongate further and they also shrink much more decisively. Okay, so this is something that would have guided you towards selecting appropriate coefficients when we would speculate about what the length at UTS would be. Again, it's a minor observational error, not a major one. Okay, then you would need to estimate the engineering stress and engineering strain, using your values, and true stress and true strain using your values. What I found so far is that you could do engineering stress and engineering strain well. So engineering stress is force divided onto the original cross-sectional area, right? So, and when we think about engineering values, they're a bit of a, for lack of a better word, they're flat earth values, all right? So we only consider unchanged cross-sectional area of the sample. So we apply the load, but we assume that the cross-sectional area remains constant. The true stress assumes that the cross-sectional area dynamically shrinks, and it shrinks from the yield point, which means that we will have a divergence of stress and strain curves, and the engineering stress and strain curve will be lower in amplitude or magnitude compared to the true. So a lot of you have picked that point up, so which is correct. But one small error actually crept in based on the true strain and true stress. True strain and engineering strain. So engineering strain just takes the relative dimensions of your sample, at fracture relative to the original. And the true strain is the natural logarithm. So normally the natural logarithm will overestimate the value of engineering strain, which means that the engineering strain true will be slightly larger than the engineering strain. Okay, so sorry, not the true strain will be larger than the engineering strain. So in a way, you have both stress true being elevated over the engineering stress, and this true strain also being elevated in terms of magnitude relative to engineering strain. So some of you got it correctly, some of you missed, not by a long shot, but by a small fraction. Okay, not a big deal. Nonetheless, still an error, something that I would, like if you would plot, if you would calculate the values and you would plot it, I would still, like if I would be marking, I would still give you marks, maybe not full marks, but I will reduct some for a fraction of the mark if there were some errors in this aspect. When you would plot your graphs, so there will be two divergent branches. So for one material, you will have like a line diverging over, the true stress and strain will go up, and the engineering stress and strain will just plateau out. And then another material will have also like this tweaked type of a line. Whatever material you have, the stronger material that withstanded the higher force will be higher on the graph, and the weaker material will be under that material. Okay. Then when you were required to examine and classify fracture behavior. Let's look at these images. So when we look at the images, when you have two samples together, and this is what was required from you working in the team or in small teams, you needed to contrast and compare the features in the fracture zone. So let's say when I look at aluminium and I would contrast it to, like, simply to the center sample, which is plain cold rolled low carbon steel. Let's see what we can, what visually is sort of appealing and revealing to us. Okay, so aluminium has a really sharp line, and this sharp line is a shear line that is at the angle. This angle is normally about 45 degrees. So this will be shear line, and across that line there will be real defined thinning towards the shear lip. So the edge, it's called a lip, or the shear edge. And you could use words such as shear fracture, shear angle fracture, shear lip, or defined fracture. Okay. What you also see for the in the aluminium sample, that there is almost no visible necking. Like if I would contrast it to steels, steels have necking. Aluminium, I don't see. Okay, it's a brittle fracture, or it's pseudo brittle or almost brittle, but I would classify it as a brittle fracture with limited necking behavior. Again, this is something that you could have written. If we look at copper, the reddish sample, what you see is that again there is a shear fracture, slightly not at a normal angle, like not a sort of flat or horizontal, but at a slating angle. And then you see not a strong necking, but still defined thinning closer to the ends of the neck. You see a reduction of thickness, not within the shear lip area, but it's actually extending further into the bulk of the sample. So it's almost like, you take a pen, or like if you are sharpening a pen or a pencil, right? You want to cut your pen or pencil, so it actually the cut is almost like at infringing angles. So the angle should be small enough so the pointy end is sharp and elongated. So what you see, for example, in the copper sample is that there is a defined thinning of a width towards the fracture zone. Then it depends what type of sample you have and how observant you are. Some copper samples may actually even display a bit of cup and cone. So cup and cone is what you see in the middle sample, like you have a little bit of depression in one part of the sample and a little bit of an extension in the other part. So it's called like a cup and cone fracture. When we look at metals, the non-stainless steels, so annealed and cold rolled, they display quite a defined necking, right? And this necking is extended from the shear zone some distance away. So it's not, it's not coming from the T clamps or T flanges, but it's actually quite localized. When you look at stainless steel sample, there is still enough. So let me, don't know if I can. Yes. So if you look at the, no, I can't zoom any further. So when you look at the fractures, you see how different the fractures are. So the middle sample has a little bit of a cup and cone feature. There is a defined thinning around in the middle. Copper and aluminium, they almost have no necking. Aluminium, like doesn't have any pronounced necking, while copper has a little bit of thinning at the edges. So what you could also see is that there are some fiber-like ends or fibrous ends. We could use the words as fibrous ends or fibrous connections. And at the end, what is important is to differentiate between more brittle and a more ductile fracture. So what I've spoken about in using words, something like this. I mean, you don't have to write sentences, but you could have used 4, 5, 6 words that are descriptive enough that could cover shear, thinning, necking, shrinking, elongation, fiber, the localization of the fracture and so on. Okay, so if you wrote something like that or along those lines, you would get full marks. So far, the reports I've seen, they were not very convincing in terms of the language which was used. Okay, let's then look at the individual questions. So there were 3 individual questions, which are constructive answer, and then we also had multiple choice questions. So I'll read out the individual answer questions. So question 1, using the values from table 3, which listed ultimate tensile strength, fracture strength, percentage elongation, and percentage of reduction of cross-sectional area, compare the ratio of fracture strength to UTS for the 2 materials. What does this ratio indicate about necking behavior and strain localization prior to fracture? Relate your answer to ductility and fracture characteristics observed in task 7. And task 7 is the visual observation of the fracture behavior. Okay, so what this question really asks is that, look, you've got 2 samples. One sample displayed larger percentage elongation longitudinal, and that sample would also display larger reduction in percentage of cross-sectional area. Okay, that was a ductile sample. Another sample would have less or smaller values for percentage of elongation, so it would not elongate as much, and also it would not shrink as much. So if you compare the ductility displayed by both samples relative to the ultimate tensile strength, what question asks you, does it mean that strong materials are ductile? Or does it mean that weak materials are brittle? Well, not really, but if you would contrast, for example, aluminium and stainless steel, so what you see is that aluminium is a weaker material and it has inferior elongation, longitudinal, and it has inferior reduction in cross-sectional area, so it does not really shrink. Okay, so it's a brittle material and it's a weak material. This is something that you should be able to identify. Contrasting to stainless steel, it is a stronger material which is more ductile. Okay, you need to take the dimensional change and relate it to the mechanical behavior of the material. So if you can contrast it well, that's great. Secondly, what is important is that you see if a material, so we're pulling materials apart in tension. As we're pulling it, so we initially tension the material and it's elastically deformed, then it starts to plastically deformed, and then it sort of deforms up to the necking point, and then we start to descend into the fracture. So normally the descent from the peak to the fracture, brittle materials, they have very, very little descent curve. So that from the ultimate tensile strength to fracture, it's rapid and quick and very low movement. While ductile materials, normally they will elongate, start necking, start shrinking, and then fracture. Okay, if you could catch that point, that will be great. But so far, I have not seen anyone noticing it. While that's, again, it's, you need to be a little bit seasoned by, by looking at the samples and seeing the data. In the past, I have seen students picking up that particular characteristic in samples, but you need to have maybe a bit of a keen eye and a bit of an inquisitive mind as well. Okay, so imagine you have a really brittle sample, right? So a brittle sample will be like a brick or glass or brittle polymer. So it will extend out and it will not elongate, it will just break at the ultimate tensile point. Okay, that's a brittle behavior. But any ductile material will reach the plateau, start thinning at the neck, and then descend down. Okay, so that's another indication. So the difference between UTS and fracture indicates how brittle materials are. That's what this question required. Okay, question 2. Using percentage elongation and percentage reduction of cross-sectional area from the samples, determine which material exhibits greater ductility. Discuss whether both indicators lead to the same conclusion, and explain any discrepancies in terms of deformation behavior and necking. Relate your answer to fracture characteristics observed in visuals. This is what we just discussed. So what we looked at in the first question, we look at the fracture strength in UTS. So the fracture strength, if it's close to UTS, it's brittle. If it's further removed from UTS, it's more ductile. So that's a giveaway. The same thing is about percentage elongation and percentage reduction cross-sectional area. Ductile materials, generally, as a rule of thumb, they display both longitudinal and also shrinking behavior. Brittle materials, they can extend less, but normally the RA or shrinking is quite small as well. So contrasting them will give out a behavior of the materials and will classify one as more brittle and classify one as more ductile. Okay. And again, when you ask to explain any discrepancies in terms of deformation behavior in necking, so deformation behavior in necking is that if there is pronounced necking, so the materials with long, like with significant percentage elongation and significant percentage of RA will always have defined necks, will always have significant visually visible thinning in the fracture area. Materials that have small values in percentage elongation, in ductility, and in shrinkage will not have defined necking. Okay, so again, that question was really asking you to be observant of what you see and trying to correlate physical data values to the visual observations and mesh them together and have cohesive and coherent story. Okay, question 3, using values from table 5, which is engineering stress, engineering strain, true stress and true strain for both materials, explain why the difference between engineering and true stress increases with plastic deformation, and discuss which material is more affected and why. Again, this is something of a fundamental nature. So the material that is the most ductile will have the highest, so because it's most ductile, it elongates the most, and also the cross-sectional area or the neck shrinks the most. As the neck shrinks the most and its gauge length increases, the strain in that material will increase significantly. So, and this is another factor which the question asks. Again, I wrote down these questions trying to connect the visual observations, what you would see in materials, to your physical values. Again, if you would take the values not necessarily as elongation and thinning, but also stress and strains, they tell the same story. The true stress and strains will be significantly higher in magnitude for those materials that have the highest ductility. Okay, that's another regurgitated effort to force you to look into the fracture and the behavior of the materials and try to recognize that data tells the same story. And data in terms of ultimate tensile strength, fracture strength, stress, strain, elongational ductility, and shrinking. Okay, so it's all the same. Right, let's read through multiple choice questions. And they're actually fairly easy, fairly straightforward. So first multiple choice question, I'll read out the question and then all options. Which statement most accurately defines yield stress in engineering materials? A, the stress corresponding to the onset of measurable plastic deformation following linear elastic behavior. This is the correct answer. Okay, this is the stress. So this is X and Y axes. So elastic region, plastic region. The yield, this is where the transition happens. So that is the correct answer. Then option B, the maximum stress attained prior to necking. Stress localization. No, this is incorrect. Option C, the stress at which permanent deformation occurs after fracture initiation. Also not correct. Permanent deformation indeed is starting at the yield point, but the caveat here, after fracture initiation, the yield is not where the sample fractures. Okay, sample fractures at the tail when it's already passed through the ultimate tensile point, and it's been elongated or stretched or compressed, and it's to the point of failure, and then it's fractures. Okay, so that's also incorrect. And finally, the stress D, at which elastic deformation becomes non-linear due to atomic bond stretching. No, this is incorrect. Okay, so that was an A answer. I see that it's half-half. So from the reports that I have marked, half got it and half are missing out. Okay. Second question, multiple choice. How do structural defects such as dislocations, vacancies, grain boundaries most directly influence the stress-strain behavior of crystalline materials? Okay, so you see the question itself is a bit tricky. So we are focusing on crystalline materials, not amorphous. Okay, so it's not polymers or anything. So crystalline means ceramics or metals where the structure is crystalline. So, and these materials will have defects. Defects means like cracks, voids, anything in between the grains. So option A, defects increase elastic modulus by strengthening interatomic bonding. No, defects are bad. Okay, they can't really strengthen. So that's wrong. Option B, defects facilitate plastic deformation by enabling dislocation motion, typically lowering yield stress. This is the correct answer, okay? Because if you have a void, or if you have a point, line, or slip defect, what it basically means is that you allow grains to slide relative to each other, okay? So yes, the connection is broken, the connections between the grains are compromised, but in a way where defects making the material weaker, which means, and what it means, like if we are to, like I hold the pen, right? So I apply a force and I try to bend it, and the pen resists and resists elastically. And if I apply significant force, I will bend it. And if I have more defects in the pen, I have lines, cracks, whatever, they will allow me to use less force, right? And this is the correct answer. This is what it actually means. So lowering yield strength. Yield is the plastic deformation. So yes, lowering yield strength, meaning weakening the material when it starts to deform plastically. Okay, so the B is the correct answer. C, defects prevent plastic deformation by restricting atomic movement. No, that's wrong. And option D, defects increase ultimate tensile strength without affecting ductility. No, that's nonsense. Okay. Last multiple choice question. Oh, by the way, so far I see everyone got this question correct. Okay, so I haven't seen the wrong answers so far. Last multiple choice question, which statement best describes the modulus of resilience? So resilience is really how much energy material can park or absorb without breaking, right? So think about, we want to have resilient springs. We want to have resilient structures that deform only elastically and don't deform plastically. Okay, so we're only looking at the area up to the yield point and no further. So we're only working within the elastic region. So modulus of resilience, which statement describes it? A, the total energy absorbed by a material up to fracture. No, that's wrong, because fracture is where both elastic and plastic deformation already had at play. Okay, so no, we don't want material that already been plastically deformed as a spring. Option B, the energy absorbed elastically per unit volume up to the yield point. This is the correct answer. And so far, I see these correct answers is in most of the reports. Okay, option C, the energy absorbed during plastic deformation prior to necking. No, that's wrong. So basically it says, or between yield point and necking. No, that's wrong. And option D, the resistance of a material to cyclic fatigue loading. Yeah, to a degree, but it's really more fatigue resistance rather than modulus of resilience. Okay, so that's also wrong. That's it. Any questions? I think we've ran through 45 minutes. That's a bit, yeah, that's a bit long, but hopefully it answered some of the questions you may have. How we can best prepare for next labs? Okay, so maybe I'll close the recording.